Welcome on behalf of EMMC to this webinar today. This is in our series of webinars from our organizational members, and today it comes from Fraunhofer IWM. So with that, I would like to welcome Yoav Nahshon, who's from IWM, the Fraunhofer IWM Institute. And I very much look forward to the talk. It's entitled Semantic Orchestration and Exploitation of Data for Materials Manufacturing Process and Products. What I just want to say here, of course, apart from the topic being of very wide interest, we also see here a really fantastic example of how quite a number of European projects and also national projects have worked on this topic and, have led to what we are going to hear, this data space management system. And so it's a great example of how the community and different contributors work together on solutions that are really important across the board for all of us. So with that, welcome, Yoav, and we'll look forward to your presentation.
Thank you, Gerhard, and thanks everyone for joining today. I will share my screen. Okay. Then in today's talk, I will present some of our activities. But first, let me start by introducing Fraunhofer. So Fraunhofer is a leading applied research organization in Europe, founded in 1949 and named after scientist Josef von Fraunhofer. And it focuses on application-oriented research. So it's translating scientific research into practical solutions for industry and society. It has global impact and innovations with over 30,000 employees, primarily scientists and engineers, and research budget over 3 billion euros. Where 2/3 are funded by contracts with industry and government. And the key areas of expertise is health, energy, manufacturing, AI, and mobility. If we look at this map, we see many institutes of Fraunhofer, and we are located right here in Freiburg. And our institute is called Institute for Mechanics of Materials, and here we are specialized in materials of mechanics and performance. Founded in 1971, a bit over 300 employees. And here we are trying to bridge the science to the industry, where we also offer practical material solutions to enhance product performance. We collaborate closely with the industry, such as automotive, aerospace, energy, and manufacturing. And we have key research areas such as material characterization and testing, failure analysis, damage prevention, simulations, modeling, and of course, also digitalization. And this will be my topic for today. So specifically to the activities of my team. Which is called Materials Informatics. Here we have, we can roughly say 4 focuses of interest. One is data space, where we want to organize and manage data and enhance data-driven research. We also have digital ecosystems such as virtual marketplaces for having efficient materials data exchange. Also, ontologies is an important concept for us to ensure a consistent, standardized representation of data. And AI application is also important with the generative AI and everything that is going on at the moment. And all of this is useful to optimize strategies and design of materials and new products. So that was a small introduction on us. And now I would like to dive into a research project where I would use it as a showcase to show some of our actual activities and technologies. So the project is called Stil digital. In German, it's Stahl digital. And the title translated here is ontology-based interoperable workflows for the development and optimization of steel materials for component use. So from semi-finished sheet metal production to crash safety. There we have had three partners. It was a German project financed by the government. We had the Max Planck Institute for Sustainable Materials, INFI in Leipzig, and us in Freiburg. The project ended this year. And here I would like to show you what we did there. So just to get started, we had, let's say, a common process chain in production, where here you can see on the right-hand side, going from hot rolling to cold rolling, heat treatment, component production, component use here in a car. So this would be somewhat typical, specifically if we want to develop new steel materials. There we have some parameters that we would like to optimize, such as performance and particular properties that we are interested in, sustainability and resilience. And of course, as nowadays it's becoming more important to keep track on carbon footprint, so we would like to reduce that. There we are also speaking about hydrogen steel and recycling, and this will lead to some challenges. And our hypothesis is that orchestration and exploitation or semantic exploitation of such data is highly beneficial. And so the project aims was to develop the domain-specific ontology for the steel materials and relevant process chains, and then also workflows and simulation tools in an ontology-based data space. And this is what I will show. So the overall process that we see here is that we have the manufacturing process, and we have different products going into different processes, and each step may have some more information. And then we can do some, for example, some tests. So here, after with the specimen, we can do a tensor test, and we get some data. And this kind of process that is following what we see here on this picture is what we will try to represent in our data space. Let's first talk about some challenges. And here we, of course, in the world of manufacturing and material science, there are lots of heterogeneous data sources with different data formats. Workflows are often complex. It's rarely never just one step. It's always multiple steps. And we also want to keep track of that to understand from where our data comes from. And we also are aiming to have fair data, so findable, accessible, interoperable, and reusable, to increase the value that it stores within. What we see here on the right-hand side is again the process, and here we see the translated data process that comes with it. So when talking about hot rolling, we also have some data related to that one, and so characterization and so on. And this goes into, we can store some parameters. It goes into simulation data, and then this data is of course connected with each other. And then we would like to somehow consider all of that, and that requires the interoperability in the workflow. When we are getting into the topic of how we want to store the data and to manage it, we have this pyramid in mind, where we first start with the data, and this could be, for example, just a number coming from a data sheet, but then we can go up in the hierarchy of semantics, and we say we have the information, and here we know that this number is actually a measurement value of, in this case, the tensor strength with megapascal as measurement unit. And the knowledge, if we go up a bit more, we also know, we can say that it's part of a norm, isonorm, with related to this specimen and a material, the DX56 is a specific type of steel. And this one has this tensor strength. And if we go even higher, we can make predictions. And for example, here we can say that the drawing depth is can be this value, 67 millimeters. So, and our approach is to start with the data and then go up to utilize as much as we can from it. And to quickly say what we mean by semantic technologies and knowledge graphs. This is just one slide to present that. It will be quite brief, but here we have, by saying knowledge graph, we are usually referring to these RDF triples that we store in a triple store. So that's a specialized database for RDF data. And here we have the nodes, which are concepts that we have, and they are connected by relationships. So, for example, component is composed of the X56, which is a material, and it has tensor strength, and this tensor strength has value and unit. So every part of this this triples component composed of, and this object, this DX56, is a triple in the triple store, and together we can construct a graph in this way. And everything has an IRI. So for example, here we have an example of a QEDT IRI for megapascal. And then this can be used for both humans and machines. And humans is also useful because they are in many different books or different contexts, sometimes the same. We mean the same thing, but we use different terms. So having a term that can refer to, can have many synonyms, can also be very useful. And this we can link to existing data, such as data sheet coming from a measurement machine. So the benefits of using such technologies is that it will help us to adhere to the FAIR principles. It also is relevant for having AI-ready data. So that means that if we need labeled data, those kind of annotations and enhanced data representation is very useful for that purpose. And then we can also add data sources, and because we are creating this additional semantic layer, we are becoming independent of the original format and structure. And this is also very useful for tracing back information and where it comes from. This is specifically relevant for material science, where we often want to know the data that we have, how credible it is, what is the quality of the data. And for this, we often want to see where it comes from, and so we can see ourselves that it's actually useful for us. What are the challenges? So it doesn't come for free. It does require additional effort and resources. So it is rather complex to manage all of that. And then it's the ontology creation and the infrastructure. It's rather could be quite cumbersome. And here we try to offer our solution to manage and handle those challenges. So what we propose as a solution is what we call the Data Space Management System, or DSMS for short. We refer to it as our approach and as well as a solution that is implemented as a technology stack. So we call the DSMS technology stack that powers data spaces, because we can have different types of setups with our technologies and modules. And with that technology stack, we power the data space, in this case for the project State Digital. And again, we have the challenges on the left, and on the right-hand side, we see the 4 pillars of the DSMS and what it offers to do. And just going one by one with data integration. Here we have a tool that is called Data to RDF, which is available also on GitHub. It takes data from measurement machines. In this case, we see tensor test data in a CSV form. On the upper side, there is some metadata. In this case, it's in German. And then we have some time series data on the lower part. And with this pipeline, we are able to convert this data into RDF representation of it. And this means that if we had before German terms related to some values, now we have it using the concepts coming from the ontology or vocabulary. And we can see here, for example, that we can now refer to that to those terms, and it becomes clearer what's happening. Those vocabularies were also gathered in the project. This was done by Infi, and I will show at the end how we do it. So that's related to the harmonization of data. We also have what we call a form to RDF. So to make it even simpler, we also allow admins or some users with elevated rights on the platform to create web forms. No code required, so it's an interface that allows to create those web forms and mappings to these ontology terms that we've collected. And then users can see this kind of form, enter the data, click submit, and behind the scenes, this data is converted to RDF and then can be rendered in this way for visualization. Next, when we talk about data exploration, we would like to discover the data that is stored in the system. So here we can use, again, the vocabulary to find stored information. And here we are searching tensor test. We can find all the related data sets and or testing machines in this case. And we can also have a Sparkle console to query it further. The Sparkle console is optional, is only for users who would like to use it, but for most users, they don't have to know Sparkle in order to get around the system. For tensor test or for data specifically, what nice is to have is here we can see how the data is connected, which is a bit hard to read, but it's also useful to have the RDF representation of the data, because then we can have such visualizations, and because it's the data is harmonized, then we don't really care how it came from, which format it was. We can simply make those visualization analysis just using the enhanced representation in a very straightforward way. This I will show later. And once we have collected all these data sets, we can, for example, have we want to compare all the relevant tests and see how they perform. And so we can create such diagrams with all the related materials, and then we can say, okay, these materials or this group of materials are relevant for my product, and then I can explore them further. When it comes to new knowledge, once we have some knowledge in the system, we would like to create some more. We have the possibility to create more knowledge from the existing knowledge we already have. For this purpose, scientists often like to use Python, and here we offer our Python SDK that allows programmers to easily access the data and use it from Python. There is a documentation for this. And then we can create scripts to take the data sets, for example, and generate workflows. So here, for example, we have data sets connected to a testing machine, and then we can create material cards. And one of the results of the project is the semantic material card, where we have the data sets with their enhanced representation in the system. We can have some apps. We use Argo and Kubernetes to orchestrate these apps. If these are some technologies that are useful for us, but for the user, they don't necessarily need to know about them. And then we can take those semantic data, create other data. So here it would be some parameters and properties also represented in RDF. And then we can, using another app, we can export them to specific material cards. So these are used for simulations. For example, in LSDyna, we would need to have data in this format, but we can then simply export it from the semantic representation to the specific format of LSDyna, and we can use the specialized app that is for that purpose. Here it's just a quick look on Argo and Kubernetes, how we orchestrate these kind of processes. This is somewhat hidden from the user, but we are using it, and we also hope to make it even take a stronger role in the future. So now we have those capabilities, and the question is how we would like to set this up. With this technology, we can have powered data spaces in different ways, so different emphasis on the modules, but we can also have different types of setups. So we can have a local data space, and this can act somewhat similar to an electronic lab notebook to store data from the lab. But you can also have it. So this will be inside of a company that will serve the members of that company or organization. We can have a public data space for everyone to access and to share data. And then we can have some kind of maybe across multiple companies, and we may have some tools such as the data space connector, as we see in the initiatives like GaiaX to exchange data between data spaces. This we don't have yet, but this is something that we are interested in to look into. So just a quick summary before I jump into the demos. We have collected extensive collection of materials, roughly 100 experimental measurements integrated into the data space in a fair manner. And we also have this representation in the data space, and as well as simulation workflows, and the development of apps and semantic material cards are also part of that. And what comes next is that we have some validation with the industry. That's what we are currently aiming for. We want to increase the usability and the development and the materials engineering, and also to include generative AI tools as part of it. So, for example, a chatbot would be very useful, and we are also looking into that. At the end, the goal is to empower material scientists to use semantic technologies. So let's see the demo. I will go to my browser. So this will be the instance of our data space, the still digital or Stahldigital in German. After I'm logging in, I can go to the knowledge. I can create a knowledge item. I will do this a bit later. First, I will go to the explore page, and let me find my manufacturing process, so I can here get all the manufacturing process. Okay, I need to log in again. And now I can see several manufacturing processes. What we were interested in, what we showed in this slide, was the hot rolling for this material, the X56. If I go to this material, since I'm an admin, I can see it as an admin. If I want to see it as a member, this is what a member will see it like. So I don't have the ability to edit this. Here we have a summary. There is some kind of information about the process itself. I can see the, so as I said, this form is being converted to RDF. I can either download it and see how it looks here, or I can also visualize it in this way. So in this case, it's quite simple graph. We can then have apps and annotations. I would skip a bit about that. I want to show the graph view. So here we have the different resources that are connected. And if I increase the depth, then what I have is that I have the entire process. And we have the hot rolling and then the semi-products that are coming from those processes. And I can then see how this looks like. We have the blanking. This goes into the deep drawing, which would end up in the as a component. But you can also have some tests, and you can do some wire cutting to get some specimens. And from those specimens, we can derive some. We can do tensile tests, and then we have data sets for a tensile test. So if I go to this item, then I see the data set and all the properties. And here it's again this analysis. I want to show it just in a bit. So let me just do quickly the process of creating a knowledge data set. So I can just go here. I can say my data set, and I say it's okay. Again, I have this view, and I can attach an app. This I can do once, and for all the files that I will upload. We are, yeah. Okay, I can trigger that one just when I upload the file, I save it. And now let's have a look at this file that I have here. So this is again the a typical file that can come from a measurement machine. So here again, we have some kind of information about the institute and the material, and you can see it's in German. So maybe it's okay if you know German. It could be a bit more difficult if not. So that's why, again, the vocabulary is useful. So if I now upload this file, then I can have the app running, and then we have this pipeline running behind the scenes. And I have to wait a bit. Okay, now it's done. Now we have all the data in place. We also have measurement unit. It's not shown here. It's in the knowledge graph. This is a small problem that we already have fixed, but not in this version. And here we have the representation here, and we can do some analysis. And here we are using directly the vocabulary management that we that we have, so we don't necessarily care about the original names. We can use this kind of terms from the ontology, from the vocabulary. Maybe just to quickly show you what we have here. So we have in this page, we have the knowledge items. We can create more. And as a user with an elevated rights, I can do it from here. And then I can create, let's say I can create manufacturing process, and I can have this form, and this form I can simply do it here, where I can define the different properties. So for example, I can say I want to have another text field for, let's say, company, and now I can give it some information. I can save it, and then it's just here, and I save it, and it's becoming part of the form that is available to the other users. We also have integrated Jupyter that users can use to access the data with the SDK that I spoke before. This is the documentation, so they can do it directly from here. Let me go back to the slides. There are a few last things that are relatively important that I would like to show, and then I will finish. So what we have here is the vocabulary in ontology management. I'm not showing it on the platform because it's relatively new and not yet integrated, but what I would like to show here is our interface to handle these ontologies that are used by the system. And here we see that we have, these are the ontologies that are there, and we can see the terms, and this will be the user interface for that. We can search a term, and for example, the Young's modulus is there, and we can see some information about it. And that will be it for that one. Here I can show how we create a namespace. So let's say I want to create, I want to create a new vocabulary for my use case. I can do it in this interface where I can give a version. I can say it's modifiable, so I can add some new terms to it. Here I have to provide a base IRI. So as I said, each term in the Jupyter store must have an IRI, and therefore this is the best IRI for that. Now it's there. We can see some properties about it, and we have the use cases. So the use case we use to gather some information. How to cluster information together. We can have some configurations on how what kind of information we would like to have for this for the vocabulary. So this we see here. I will skip a bit. So here we go to the table. Okay, let me go back a bit. I'm back to this interface. I can select now my namespace here, and then I can add a term in this way. And again, I'm using the form that I created before. And I can say it's, I'm not sure if it's a property or, so I have different types of property, but I have this generic one if I'm not sure. I save it. So I created before a car, I created a has part, and now I would create another term for a wheel. Maybe later I would like to say a car has part wheel. So I can do it in this way. So I can just use it, and I can, now the status is pending. I would run the pipeline, and then these terms will be converted, will be added to my Jupyter store. It takes some time, and to skip it, I will go to the next video to show how this looks like. So now it's done, it's published. Now we have an IRI for those terms, and I can export it to an Excel sheet, which I can open. and I can also edit. I can also import it back. But these terms are now in the triple stores, and I can now use them in my workflows, in my annotations. The last thing I want to show, and then I will really finish, is talk a bit about the CADA. So we have a long demo here. I won't show everything, but this activity is relevant for this forum when we talk about the European projects. So CADA is quite an interesting initiative that we have from the projects Oyster and NanoME Commons, which is still running, would be ending soon. Here we are trying to create how to create an interoperable and standardized characterization protocol. And for that, we use the Cameo ontology. And we have this interface. It's still in development mode. So we do want to make it public for the community so they can try. So all of us, we can try it out and see how useful it is. But here, basically, the idea is to create some kind of an online documentation, which is also interoperable for processes. And this is just how this process looks like. So I have the web forms, and as I go forward, I create this graph, and I can continue, and I can connect the steps that I do at the lab with the different information, the calibration data, so on. I have some properties. I have maybe some sample preparation. I can enter that, so I can really make this graph quite big. This just video shows how this looks like. And you can see it becomes quite big. What we end up is that we can then export it into RDF. So the triples, we already store it in the system, but we also have the possibility to download it. And once it's there, we can search for it. And for example, the user case that we created, it's there with some information that we entered before. And that's how we do it. This is also would be extended to the MODA, as we know from previous projects. That is our plan. Okay, so with that, I would finish. You will have more information about us in the About page. You can also find us in the LinkedIn and just contact us. But that's what I wanted to show today. Thank you.
Thank you so much, Yoav. Really fantastic work. As I said, we will just the presentation, not the discussions and so on, make that also available. So hopefully we'll get even more people listening to it and more discussions going online. Thank you.
Thank you, and thank you, everyone.